Imagine sending the same signal into a system today and then sending the exact same signal tomorrow. Should the system produce the same response? In many engineering applications, consistency over time is essential. This important property is known as time invariance, and it plays a major role in signal processing and RF system analysis. In engineering, systems are often expected to behave consistently regardless of when a signal is applied. If the same input signal produces different outputs at different times, predicting system behavior becomes extremely difficult. Engineers would need to constantly monitor and update system models, making analysis and design far more complicated. Consider a communication receiver that behaves one way in the morning and another way in the afternoon, even though the same signal is applied. Such unpredictable behavior would reduce reliability and make performance difficult to guarantee. Modern communication systems depend on stable and repeatable operation. The challenge is determining whether a system's behavior depends only on the input signal itself or also on the specific moment when the signal is applied. This leads directly to the concept of time invariance. A system is called time invariant if shifting the input signal in time causes an identical shift in the output signal without changing the shape or characteristics of the response. In other words, the system behaves the same regardless of when the input is applied. The key idea is consistency. A time-invariant system does not care whether a signal arrives now, later, or earlier. The only difference is that the output appears shifted by the same amount of time. The underlying system behavior remains unchanged. Mathematically, if an input xt produces an output yt, then a delayed input xt must produce a delayed output ytt. When this condition is satisfied for all delays, the system is considered time-invariant. Intuitively, a time-invariant system behaves like a reliable machine that always performs the same task regardless of when it is used. For example, if pressing a button today turns on a light, pressing the same button tomorrow should produce the same effect. The timing changes, but the behavior remains identical. Physically, consider an ideal RF filter. If a signal passes through the filter now, the filter produces a certain output. If the exact same signal is transmitted 1 second later, the filter should produce the same output waveform delayed by 1 second. The filter itself does not change simply because time has passed. Mathematically, suppose a system produces yt equals 2xt. If the input is delayed by 3 seconds, the output also becomes delayed by 3 seconds while maintaining the same scaling factor. This satisfies the condition for time invariance because the system's transformation rule remains unchanged. Time invariance is extremely important in RF engineering because many analytical tools assume that systems behave consistently over time. Filters, transmission lines, amplifiers, and communication channels are often modeled as time-invariant systems to simplify analysis and design. In practical wireless systems, engineers rely on time-invariant approximations when designing receivers, equalizers, and signal processing algorithms. These models make it possible to predict system behavior accurately and develop efficient communication techniques. At the system level, time invariance allows engineers to apply powerful methods such as impulse response analysis, convolution, and Fourier transforms. Many modern RF technologies would be significantly harder to analyze if system behavior changed continuously with time. Although time invariance is a useful assumption, many real-world systems are not perfectly time invariant. Component aging, temperature changes, battery depletion, environmental variations, and changing wireless channels can all cause system behavior to vary over time. A common mistake is assuming that every communication channel is time invariant. In mobile wireless systems, for example, moving users and changing environments can cause channel characteristics to change continuously. In these cases, time-varying models become necessary. The concept of time invariance forms one half of the foundation for linear time invariant systems, commonly called LTI systems. Combining linearity and time invariance creates one of the most powerful frameworks in signal processing and prepares us for impulse response and convolution analysis. In this lesson, we learned that a time-invariant system responds the same way regardless of when an input signal is applied. We also saw how this property provides consistency and enables powerful analytical tools used throughout signal processing and RF engineering. In the next lesson, we will explore impulse response and discover how a single special input can completely characterize an LTI system. If you found this useful, like the video, subscribe, and follow for the next lesson.